Good morning, everybody. It was great to see you before they put the lights down. It's really wonderful to see so many people here in the audience and so many people of so many ages to this special event. And it's kind of nice to see the sun peeking through, isn't it? Well, thanks for joining us here on the University of Michigan campus, and those of you who are joining for our online stream. Welcome to another special Saturday morning physics event. Well, all Saturday morning physics events are special, but this one is special in a special way, as we shall soon see. I'm physics professor Tim Chupp, one of the organizers of Saturday morning physics, along with my colleague, Professor Roy Clark, and Carol Raybook, and Monika Wood, and her staff of the Warren M. Smith Demolab, who will be giving the presentation today. Saturday morning physics is a unique opportunity for our department, the physics department, to reach out to the community, bringing the excitement and the impact of science, not just physics, to the broadest possible audience. Often, hundreds join us in person, as you are here today, and online Saturday mornings to learn, to take part, and to enjoy. Many of you are regular Saturday morning physics patrons, and many of you are here for the first time. Who's here for the first time? Wow, look at all those hands. Welcome. Well, we hope you'll continue to join our events. How many of the people here in the audience were at the event about 2 months ago when we had astronaut and physicist Josh Cassada from the International Space Station live? Okay, well, that's a pretty good show of hands as well. There were quite a number of people there, and I just wanted you to know that early this morning, about 2:20 a.m., the Dragon capsule piloted by Josh left the space station and will actually be touching down on Earth at about 9 p.m. this evening. So that's pretty exciting, and yet another great connection of Saturday morning physics. So, I do want to take a moment to acknowledge the financial support of the Saturday morning physics patrons. Many of you, so many individual members of our audience and so many fans, and we're also very grateful to have the support of the Dr. Mary Lois Tiffany Endowment, the Hidekio Tomizawa Endowment, the Van Loo Family Endowment, and the Walker family. So today is special because we have the staff of the Warren M. Smith Demolab showcase and explain a number of demos that illustrate how energy changes from one form to another. We decided to call it Physics Goes Boom for reasons that you can just imagine and will soon experience. Lecture demonstrations that illustrate quantitatively or qualitatively concepts taught in physics and other science subjects have been an academic tradition for centuries. The University of Michigan, with thousands of students studying physics each year, has a premier collection of demonstrations that are actually stored in a room just below where you are sitting here. So don't worry, they're actually disarmed before we store them, so everything should be okay. So the UM has a premier set of experts managing that collection, which is called, as I said, the Warren Smith Demolab, in honor of the longtime head of the shop. Warren had many assistants, and surely the best of those was Monika Wood, who leads our presentation today and has followed Warren as the Demolab manager. Monika came to the Demolab in 2010 and took over for Warren in 2016. She has a bachelor's and master's degree from EMU, and she did her master's thesis on changing and discharging of Lichtenberg electrets. Monika seems to have endless energy, providing demos for instruction, for export, for presentations at local schools, and many, many more things that she does. And developing new demos and putting together presentations like today's. Nick, Arnold, has a master's degree in plasma physics from Eastern Michigan University. He came to the Demolab in 2017 after teaching undergrad physics at Henry Ford College, Washtenaw Community College, and Eastern Michigan University. Nick has myriad interests, including running, rock climbing, and drumming, and he was one of the founding members of the Detroit Lions drum line. Pretty amazing, yeah. Conor is the newest Demolab staff member. He joined just about a year ago, and he has a bachelor's degree from Eastern Michigan University as well. Conor is also a climber, and he is a cyclist, yay. And also, as you will soon see, he's on his way to being an accomplished musician, on his way. So, we're really looking forward to the show. Monika, take it away.
Thank you very much, Tim. I want to welcome you all to Saturday Morning Physics. I really appreciate seeing all your faces. And we are going to take you on a journey of energy and action, so I really hope you enjoy it, all right? So without further ado, let's get started. Our discussion today is going to begin with defining some terms so that we're all on the same page and we're speaking the same language. After that, we're going to look at some energy types and examples of those energy types. And then the remainder of the show is going to be an exploration of energy transformations using the various equipment, as well as some personal experiences from each of you. All right? So we first must start with what is energy. A lot of us have an idea of what energy is, but the nitty-gritty details of how energy works is actually pretty difficult to understand. And so instead, we're going to show you examples and show you how we measure these energy transformations in these various situations. But if I really had to come up with a definition of what energy is, it is simply the ability to do work. Okay? Energy is anything that can do work, has energy. It's all around us. It takes many forms, and we're going to see a bunch of that today. Okay. Why is energy important? Very simply, without energy, there is no life. You would have a real hard-pressed time to find a situation where life existed without energy. Okay, I told you what energy was. It's the ability to do work, but what is work? We all have an idea of what work is. We would say something like, it takes a lot of hard work to get good grades in school, but in physics, work has a very specific meaning. What work is the force applied on an object through a distance. If we can easily represent that with a simple equation. Work equals force times distance. Now, force is measured in newtons. Distance is measured in meters. Therefore, the units for work are very straightforward, Newton meters. But this is also referred to as joules, which is what we will use moving forward. Okay, so let's keep this equation in mind as we move through this next exercise. I'm going to give you examples of where work has been done versus where work has not been done, again, according to physics. So let's begin with a stationary block. I got this block sitting here on the table. My question to you is, am I currently applying a force to this block? No, right? Is the block moving? No. Therefore, no work was done. What if I push this block across the table? Am I applying a force to the block? Yes. Is the block moving? Yes. Therefore, work has been done. What if I then lift the block up in the air? Am I applying a force? Yes. Is it moving? Yes. Therefore, work has been done. Now, what if I take this block and I push as hard as I can down on this block? Am I applying a force? Yes. Is the block moving? No. So although I feel like I'm doing a whole lot of work, according to physics, I did not do any work. Okay? So the biggest thing to remember with work and energy is that they are related. If I do work on an object, I have given that object energy. Therefore, that object then has energy to do work on something else. So therefore, work and energy are ostensibly interchangeable, and we can then look at that in the context of the rest of the stuff we're going to discuss today. All right.
So, when we're talking about energy, we are referring to two different types. We have kinetic energy, the energy of potential energy, in a object. So, we can further break down.
Try this one, sorry.
Sorry about that. All right, so we have mechanical energy. This is the energy of an object due to its motion. You can think of water falling into a basin, wind blowing, or even the top spinning. We also have vibrational energy on the macro scale. This is sound. This is the energy that is due to the vibrations moving through a medium. Usually this is going to be air for us. So this can be someone crying, a person singing. We can also say that someone playing an instrument is creating sound energy. Like I said before, this is typically through air, but it can exist through other medium, such as water for whale sounds. On the microscopic level, we also have thermal energy as vibrations. This is the energy that an object has due to the vibrations of its molecules, such as when something is burning, a searing hot plate, a warm cup of coffee. Even though this exists for hot objects, it also exists for things that are cold, such as for ice, because even though it is relatively cold to us, there's still some molecular vibrations. We also have radiant energy, the energy that's carried through electromagnetic waves. This can be any sort of wave, such as in a radio wave, a microwave, visible light, or even X-rays. We also have electrical current. This is the energy that's produced when current is flowing, or electrical charges are flowing through an object, such as in a lightning strike, or when you are turning on the light, the current flowing through that circuit. So for electrical energy, we also have voltage. This is the electrical energy that is stored in the device to be used for later, such as the buildup of static electricity, or energy that is stored in the capacitor. We also have gravitational potential energy. This is the stored energy due to the object's distance from the center of the Earth, such as a bowling ball for some reason placed on the high shelf, a high diver, or a wrecking ball. We also have elastic potential energy. This is the stored energy in the material due to stored energy in the material of an object, such as when a spring is compressed, a balloon is inflated, a rubber band is stretched, or a bow that is being drawn. For chemical energy, this is the energy that is stored in the matter because of its chemical makeup. This can exist for things that are man-made, like a battery cell. It exists in the food that we eat, the fuels that we burn for energy, and even living things like plants and us. Nuclear energy, this is the energy that is stored in the nucleus of an atom. We can get this energy from processes like fission and fusion. There we go. Or any other sort of radioactive decay. As you probably noticed, there are a lot of different forms. We can categorize these to make it a bit easier. So for kinetic energy, we have mechanical energy. This is broken down into both linear and rotational motion. We have vibrational energy, which once again on the macroscopic scale, the scale that we are at, exists as sound. On the microscopic scale, it is heat or thermal. We have electrical currents, as well as radiant energy. For potential energy, we have gravitational energy, elastic potential energy, chemical energy, nuclear energy, And for electricity, that exists as voltage.
Real quick, one thing that was forgot to mention ahead of time was if you guys have any questions as the presentation goes on, feel free to email physics@umich.edu, and when we finish the presentation, we will try to address as many of those as possible. Sorry, thank you.
Okay. So Monika talked about doing work. Conor gave us a list of all kinds of energies, but we don't have any idea of scale here. So the amount of work you do picking up your coffee cup from the table and bringing it to your face is about a joule worth of energy. If I were to stand on top of this table, I have about 1,000 joules of potential energy, gravitational potential energy. And we've got a few more items up here. My favorite is lightning strike. It's about 5 billion joules of electrical energy. So you could imagine a lightning strike lifting 5 billion cups of coffee to your face. One of the most repeated facts about energy is that it cannot be created or destroyed, only transformed from one form into another. So we have a little problem. When Monika was pushing that block, she was giving the block energy because she was doing work on it. But the second she stopped pushing, the block stopped. So my question is, why? Where did that energy go? Does anyone have any ideas?
It was transformed into like a work action as she pushed the block.
So she was doing work, and the block was actually transforming energy, also doing work. Do you know what it was working against? Yeah, I heard over here, friction. Awesome. So, friction is a force that works against sliding objects, and it's when you push those two surfaces together, and friction turns some of that energy into heat. So I want you to put your hands together and push them against each other. Do you feel the heat? Excellent. That means I'm not entirely crazy. This energy transformation is usually invisible to us. You can feel it sometimes. But without friction, we would have a hard time just getting around. Yeah. Every time. So we're going to look at some examples of energy transformations for the rest of the day. And we're going to start with one of my favorite demonstrations. We call him the downhill duck. So I'm going to give the duck a little bit of gravitational potential energy, and I'm going to do work by lifting him onto this ramp. Now that gravitational potential energy, it's changed his height against the ground, or from the ground. And so if I give him a little nudge, he starts transforming that gravitational potential energy into kinetic energy or linear motion. Look at him go. All right, quick round of applause for my hero, your friend, the downhill duck. All right, thanks. In intro physics, you see a lot of pendulums. And this pendulum is just a big bowling ball attached to a cable from the roof. And when I push it to one side, if you notice, its height's changing. So again, I'm doing some work on this. I'm giving it some gravitational potential energy. But when I let go, what's going to happen? It's going to swing, right? While it's swinging through the middle, all of that gravitational potential energy turns into kinetic energy, or that linear motion. And it's going to cycle back and forth between potential energy and kinetic energy, back to potential and back to kinetic. And as long as Einstein was right, as long as he's right, there should be no energy being added to this once I let go. Ooh. Okay, so luckily we're not putting any extra energy into the system, but if you look at it, each time it's getting a little further away. So where do you think that energy is going? Yeah, there's some friction, probably up at the pivot point, but there's another, I'm going to call it a loss. There's another transformation happening here. And we're pushing some air out of the way. And so every time that ball hits the air molecules, it's doing a little bit of work on them. We can also turn gravitational potential energy into other forms. I really like rotational. All right. And I think it's about this time when I should tell you, my cousin taught me my favorite yo-yo trick years ago. Spaghetti. I should probably practice more. Okay, but that's turning gravitational potential energy, plus a little work from me, into rotational motion. In intro physics, you also see a lot of oscillators. This is a big lead ball attached to a big spring. And when I lift it up, I do a little bit of work on it, give it some gravitational potential energy. And when I let go, just like the pendulum, it's transforming gravitational potential energy into kinetic energy of that linear motion. But at the bottom, when I stretch that spring, I'm also storing some elastic potential energy. And so this is going from gravitational potential through kinetic to elastic and back. A slightly more complicated system is this little mass on the spring. It's going to do the exact same things that the other ball does, except now it's starting to spin. So not only is this turning gravitational potential energy into kinetic energy or linear motion, and then it's stretching the spring at the bottom, storing elastic potential energy in a stretch spring, but it also oscillates between that in rotational motion and stretching the spring in a twisting way. So sometimes transformations can be a little more interesting. And I could watch that thing all day. Twisting and spinning. And there we go again. Now we're bouncing. All right.
All right. Thank you, Nick, for showing us those pendulum and downhill duck. However, a lot of us probably don't own a large lead mass with a spring or a duck that will just waddle down the hill. But we can witness these energy transformations in more common household items like a musical instrument. So here I have a guitar. I've been playing for a bit over a decade. And it's been a while since I performed, but I learned a song for y'all that will hopefully help illustrate energy transformations a bit more. And if anyone in the audience actually knows the song, feel free to sing along. Nervous after our first technical hiccup. All right, so that's the end of the song. Thank you. So that is the end of the song, unfortunately. However, it does illustrate energy transformations. So when I am pulling that string back, I am putting tension in the string, giving it that elastic potential energy. If I let it go, that potential energy is going to shift into linear motion, and similar to the pendulums, it's going to shift between that linear motion and elastic potential energy. Since these strings are coupled to the guitar, those vibrations will be carried down the neck into that soundboard, and the sound will be pushed out of that sound hole, both being amplified and projected. All right, let me put this away real quick. All right, so another thing that y'all probably have experience with are speakers. I have one up here. It's kind of hard to see. It's this weird looking object on top of this mess. And before I actually explain it, since y'all have had a couple demonstrations of energy transformations, I want to ask y'all what energy forms are in the system. So, the volunteer? Well, so I'll start y'all off. The energy is plugged into an outlet. It's going to be drawing currents. Does anyone know what that current's going to do to the speaker? Yep, it's going to vibrate that membrane, that diaphragm in the front. Then because that diaphragm has linear motion and is pushing air in front of it, it is going to cause sound. So if I were to turn the speaker on, it does produce a sound. So let's say I want to put something in front of it, such as a wine glass. So when the air is in contact with that wine glass, it's not going to completely bypass it. It will interact with it. So the sound waves that are in contact with that glass are going to push it ever so slightly. And I'm hoping all of you have been on a swing before. This is similar to what happens when you are trying to swing. If you are kicking too fast or too slow, you're not really going to be moving. You're going to be fairly stationary. However, if you're kicking at the right rate or frequency, that is when you actually start swinging. So when those sound waves are in contact with that glass, it is going to hopefully resonate, making the glass shift between the elastic potential energy and linear motion. So how can we visualize this? There are two main ways that I'm going to show you. First way is with a piezoelectric pad that I have right beneath this wine glass. It sounds a bit complex. All you really need to know is that it transforms mechanical energy back into electrical. So if I give it a tap, you should be able to see that there is a bit of vibrations up there. Second way to visualize this is directly just looking at it. So if I were to turn the speaker up at the correct frequency, the rim of this glass will start to move. So let's try that out. So it's not like a large oscillation, but it is fairly visible. For this next part, I'm actually going to have a volunteer come down and help me with the rest of this demonstration. You in the pink shirts. All right, first thing I want you to do are put the safety glasses on. Remember everyone, science is fun, but safety first. All right, so we're going to come over here. All I'm going to have you do is on the count of 3, 1, 2, 3, you're going to take this volume knob with the tape on it, crank it all the way up for a second, then you're just going to crank it back down. Also before that, since it's going to get very loud, here's some headphone or earmuffs. I didn't really bring a lot that many for all of y'all, so at the count of 3, I'm just going to have y'all plug your ears. And, yep, so I'm going to stand over there. I just want you to stand over here behind the splash shield, just in case something happens. All right, so 1, 2, 3. Yep. Nice job. Can I get a round of applause for our assistant? Nice job. All right, so I can take those back. And I might also need those glasses. Thank you. All right, you're all set. Thank you. All right, so as a review, since there were multiple steps to this whole demonstration, the energy transformations, it started off as electrical current coming from the wall outlet. It turned into linear motion of the diaphragm of that speaker, creating sound waves. Those sound waves interacted with our wine glass, causing it to oscillate between the elastic potential energy and linear motion.
Okay, everybody, let's look at another demonstration of energy transformation. Over here, I have a very large mass on a pulley. I'm going to give this mass a whole lot of gravitational potential energy, and we are going to see the transformation when I let go of this string. It's going to move into linear motion. Now, I'm going to give a countdown, and I'm going to let this travel its whole distance. And what I want from you is to pay attention to where that linear motion transformed into. You guys ready? Here we go in 3, 2, 1. All right, who can tell me what happened? Some of it did, absolutely. Where else might this energy have transformed into? Yeah, you. The one turning around, yeah, you. Yeah. Perfect, yes. So you definitely heard it, right? Can you guys maybe think of any other way that energy transformed?
It collided with the black part, and then the energy went to the table.
That's a good, absolutely. And now what about that invisible force that Nick alluded to earlier? What else might have been transformed into? So it created some heat, right? Perfect. Okay, so I could say it might be a little stretch to tell you that it created heat, but we're going to measure, okay? So first, we heard it, right? How did we hear it? What was our measuring device? Your ears, right? Your ears are really, really good at measuring the intensity or the amount of sound energy. If it's a quiet sound, it's difficult to hear. If it's a loud sound, it's much easier to hear. So our ears. Now, we have a way to detect heat. Many of us have had a lot of experience with it. When we want to know what the temperature is outside, we use a thermometer. That measures the air temperature. We also, if we're sick, we're going to take our temperature with a thermometer. So both of those are contact thermometers. They must be in contact with whatever substance they're trying to make a measurement. How many think it's a good idea for me to put one of those type of thermometers underneath this? This is a bad idea, right? It's going to break. So, particularly since the pandemic, a lot of us have a pretty good experience with the non-contact thermometer. And this works in a very similar way, but rather than having to touch whatever object they're trying to measure the temperature of, it uses a special type of lens that is able to see that thermal energy, which is just beyond what our eyes are able to see, which is why we need another device. Now, the one thing about the non-contact thermometer is it only measures that one location that you are pointing that at. What if we wanted a whole scene? What if we wanted to know what the temperature of that whole scene would be? Well, we have a device for that. That is the infrared camera. The infrared camera works similarly to the non-contact thermometer. Go ahead and change it. It basically takes a bunch of readings just like, and projects it in an image very similar to your camera on your cell phone, but in this case is sensitive to that thermal radiation. And so I wanted to show you a neat picture. Hello, audience. How you doing? So this is actually showing that us humans are producing this thermal energy. So we are transforming some sort of initial energy into this thermal energy. Now, what's important to note is the brighter the object, the more thermal energy it has. The darker the object, the lower that energy is. So who can tell me what type of energy transformation we are seeing with you guys? Where does the energy come from to get heat? Where does it come from? Where does it start with? Let me hear you. Food, right? Chemical energy. So it actually turns out the majority of the food you eat is transformed into thermal energy to keep your body at that regulated 98.6 degrees. And so if we move back to our demonstration, we're going to run this demonstration twice. First, we're going to show it without the camera, and then we're going to show it with the camera. So I'm going to need another volunteer. How about you on the end here? Yep. All right. And so we already talked about before that we have gravitational potential energy into linear motion into heat and sound. And so I'm going to have you stand over here. All right. And so the main difference between this and what we're going to show next is I'm going to place an object in the path of this block. So in addition to the sound and heat, we're also going to see the can deformation. Now I want you to pay attention to the level of each of those energy transformations at the end, okay? So I'm going to give you a countdown. First, make sure you can hold that. It's heavy, you got it? All right, so when I say 3, just let go, all right? Here we go in 1, 2, 3. Very good. You stay here, I got a second one for you. All right, so we clearly saw that, but I've told you that we can detect the heat that's produced in this transformation. You don't have to take my word for it. So we're going to pull up the infrared camera again. We're going to place this can, another sad pop can in the way. All right, and I'm going to give you a countdown. You're going to do the same thing. Now the only thing that's going to be different is we're going to have you stand outside of the image of the camera, so if you can take a little bit of step that way, a little bit more. There you go. All right, you ready? Here we go in 3. Oh, and this is the can in the picture, so you want to make sure that you're paying attention to this portion of the image up there. Okay, here we go in 1, 2, 3. Very nice. Thank you very much, sir. All right. So as you can see, the can has indeed heated up as a result of that energy transformation. Okay, so we're going to shift gears a little bit to another type of energy transformation. I have a coil of wire, and I have a magnet. Now, if I move this magnet near the coil of wire, something's going to happen, right? So first, I'm going to take my measurement device away. If I put this near this coil, can't see it on that, and I move it here, do you see anything happening? You see me just moving back and forth, right? You can't really see what's happening there. But if I take my measurement device, make sure that can see, and I repeat the experiment, I'm going to move my magnet near this coil. Oop. So it's clearly transforming that linear motion into something. Does anybody have an idea of what that is? Magnetism. That's the mechanism for the change. But good, good. Yes? Close, close. Electrical energy, what type? So we had 2 types, right? Voltage. So was that moving or was that stored? What was the other one? What was the other one? Current. I heard it. And so one thing that's neat about this is if I'm not moving, so if I leave it sitting here, do you see the current generated? No, I actually have to do some work in order to create that current. Okay? So that is linear motion to the electrical current. Now this next energy transformation, electrical current into heat. All of you have experienced this type of energy transformation, particularly in various parts of your house. Can anybody give me some examples of where they might see electrical current into heat?
In the light bulb.
Light bulb, good. One of you, yeah? Yeah. The stove, good. Yeah? A heater, very good. I got one more. Anybody else? Yes? Phone charger, exactly. All right, so just to recap, we've got the electric stove. We've got an iron. We've got a toaster, a hair dryer. But basically anything plugged into the wall, if current's flowing through it, some of the energy is lost or transformed into heat. So the next demonstration I'm going to show you is going to combine those two items into one. And the main difference between what I'm going to do here and what you already saw is instead of moving the magnet, I'm going to move the wire. In this case, the wire is going to be a disc. It's a metal disc. It acts the same way as a wire, but instead of moving my magnet, I'm going to move the disc. And so that movement will then create a current, and then we saw that current creates heat, right? And so we're going to pull up our measurement device. This here is my disc. I'm going to be placing this very large magnet right here, and we're going to see this energy transformation. You guys ready? Here we go in 3, 2, 1. You see the edge of that disc getting hot? All right, here we go. And so there's your transformation of, right along that edge there, electrical current into, rotational motion into electrical current into heat. Okay. The light bulb. So this was already mentioned once. We see this all the time. I'm going to specifically talk about an incandescent light bulb. So how does an incandescent light bulb work? What kind of energy transformation are we seeing? What do we start with? Electricity, right? And then what does it transform into? Light, right? And what else? Heat. Very, very good. Okay, so obviously newer light bulbs with LEDs, they produce a lot less heat, more light, but they do still produce a little bit of heat. Okay, so just to shield your poor eyes, I'm going to cover that. And this next demonstration, I'm going to utilize the heat portion of the light, of the energy transformation from the light. And I'm going to power a heat engine known as the Stirling engine. Sorry, I forgot to move this over. So the Stirling engine is a type of engine that is governed by the Stirling cycle. We could go into detail all day about that. But the main thing about the Stirling engine is that all it takes is a temperature difference to make it work. And so what I'm doing now is I'm heating up the bottom plate of this motor, or engine, and the top plate is cool. And then once that temperature difference exists, it then can create or transform that heat energy into rotational motion. And this is actually a very, very, I promise it's working. It is a very, very efficient engine, which is one thing that's really nice about Stirling engines. You'll often find these on the output of other energy generations. It's being slow today. But the one neat thing about the Stirling engine is if I flip the direction of which plate is hot and which plate is cold, oh, I must have turned it the wrong way. If I change those, all that is different is the direction of rotation of the output of this motor. So right now I put this on an ice bath. So now I'm making the bottom plate cold and the top plate hot. The temperature difference between ice in the air versus the light in the air is larger, and so we get a lot more transformation into that rotational motion. All right, and see, it's definitely going faster than when I started it. All right, so there is that energy transformation. Okay. Let's again use heat to power an energy transformation. I have a tube here. There's a screen in the bottom of the tube, and I'm going to heat it up. And hopefully you guys know that hot air rises. That's why chimneys work. That's why the second floor of a house is warmer than the basement, things like that. All right, So if I heat up that screen inside of there, it's going to allow hot air to rise, and then cooler air is going to come in from underneath, and so you're going to get this net flow of air through this tube. Now, anybody who plays an instrument knows when you blow air through a tube, you make sound, right? So let's go ahead and see that. And I can prove to you that it is indeed the airflow that is causing this to create the sound, because if I turn it sideways, it doesn't work. But if I turn it vertical, that hot air is indeed causing that sound to generate. So again, heat into sound. All right. So next we got Conor over here.
Cool tube, Monica, but I got two of them. So over here I have 2 vials filled with a solution that's mostly water. I'm going to introduce an electrical current to it. And while that electrical current is flowing through, it's going to start creating bubbles in the solution. So what's happening is that while the electricity is flowing through it, it is separating the particles into their constituent part, the water into its constituent parts, the hydrogen and oxygen. Hold on, let's correct this a bit. There we go. So let's go ahead and turn that off. All right, so let's see what happens when I put the hydrogen and oxygen in a different vessel. Right. So this probably isn't the loudest thing you're going to hear today, but I would still suggest closing your ears because I'm going to be lighting this on fire in 3, 2, 1. All right, so can anyone in the audience tell me what they observed in this? No? All right. Well, so this reaction is called electrolysis. It is a method of passing current through some sort of liquid. Here we have water and sulfuric acid, thus breaking into its separate parts, hydrogen and oxygen. So I was using electrical currents. I was able to store energy in those separated gases. When I recombined them in that bubble and introduced a small fire to it, it created heat and sound.
A few moments ago, Monika showed us that moving a magnet over a coil of wire can generate some electrical current. It seems like an inefficient way to do that, though. So I'm taking a little magnet here, and I'm spinning it near a coil of wire. And on the screen, you can see the waveform of the electrical current that I'm actually generating here. It's a lot easier for me. Turn a little rotational energy into electrical current. We can do better, though. Let's see. I need a volunteer. Now, this one's going to be a little trickier. I need someone that can fit on this bike.
You gotta be at least as tall as me.
I think if I look into the sun, right on the aisle, come on down. I think you can make this work. Yeah. All right, what's your name? Henry. Ooh, great one. Okay, hop on the bike for me. And if you see the diagram above us, this is set up as a generator. Specifically for us, we have a little bike trainer we've modified. We put a little electric car motor on it, and we're running the car motor, which has a magnet inside of coils of wire, and we're going to spin that magnet around the coils of wire, making some electricity. Okay? So I want you to just go for a little ride around the block, a nice comfortable pace. Okay, that's perfect. Now, as he's making electrical current, it's not really going anywhere, so we're going to use that to drive a load, and you're going to play the role of a electrical power generation station for a moment, all right? So now what I need you to do is keep that light about that brightness, okay? Nice and consistent, doing great. Okay, now as people come home and turn on their lights, the load in the power station goes up, right? A little harder. Okay, and for a while you can sustain it. But let's say an entire apartment building turns on. Ugh. All right, you can have a seat. Thank you very much, Henry. Big round of applause. While it's fun, I think it was a good time, I hope. This isn't a very efficient way to make electricity for large scales. So typically what we do in this country is we either use wind to turn a turbine, which then turns an electrical generator just like the bike does, and we use that wind power to make electricity directly. Or we could use a nuclear power station, which takes the heat from radioactive decays, generates steam, and that steam goes through a turbine, which is then hooked up to an electrical generator and makes electricity. We could also use coal for that. Or we can use a modified airplane engine running natural gas to spin a turbine, which is hooked up to a generator to spin a magnet inside a coil of wire, and you get the idea. There's one different one that uses the same principles, and that's hydroelectric power. So all the gravitational potential energy stored in the water in a reservoir behind a dam, let some of that water fall through a turbine, which spins a magnet inside a coil of wire and makes electricity. So no matter what we're doing, we're spinning magnets inside coils of wire to make electricity in this country, with the one exception of solar. But we'll talk about that later.
Okay, everybody, let's revisit the light bulb. So the first time that we used a light bulb as an energy beginner, we utilized the heat that was produced by this light bulb. This next demonstration, let's go ahead and use the light that is produced by this light bulb. So I'm going to put a shield in front of it just to make it easier on your guys' eyes. And I'm going to place an object. This object is known as a radiometer, and I'm going to place it in front or near this light source. And a radiometer is just a sealed container with a little bit of gas inside, and in the center of it, you will see there is a set of vanes that are rotating. One side of those vanes is black, the other side of those vanes are white. When the radiant energy, the light from our bulb, hits the radiometer, the black side of the vanes slightly warms up. The white side of the vanes does a lot of the reflecting. So there becomes a temperature difference between the dark side and the light side, and that temperature difference creates a heat differential, which then is able to be transformed into the rotational motion of this object. And it's a measurement device because if I increase the amount of light that is hitting this device, you will see that it spins faster. So bring it close, and hopefully you can see that the speed in which that rotated, because now that I brought it closer, I have more of it hitting, we can then determine exactly how much energy was transformed as a result of that radiant energy. Okay, so Nick talked about all of the electrical generation that happens in our country. The other way is through solar panels. And so this is the one oddball with how we generate electricity. And so we take our sun, in this case a very, very bright light bulb, and we let it hit a solar panel. Right now I got it hidden. And so what ends up happening is we are taking the radiant energy from the sun, and we are turning that energy into electrical current in order to do work. In this case, I have connected our solar panel to a fan. And so you're going to see that I'm going to take this radiant energy, turn it into electrical. It always needs a little bit of a start. And there I am then turning that electrical energy is now usable in various ways. And in this case, I'm just choosing to show it transform into rotational motion. Okay? And so for those of you who might have been at our last SMP, we definitely talked a lot more about how these work there. Okay. Now let's continue on the path of using radiant energy. So many of you now have an idea of what a laser pointer is. A laser pointer is just a very intense directed light source. In this case, of a specific color. So in this case, I'm going to use a red laser pointer. Now, if I let this laser pointer hit a balloon, we're going to see an energy transformation. You guys ready? Here we go in 3, 2, 1. All right. So what kind of energy transformation just happened? We started with light, and it turned into heat. Exactly. And so what happened is, although you heard a sound, that was more of the balloon's response from the elastic energy of the balloon failing because of that heat created a hole inside of that balloon, or on the edge of that balloon, causing it to pop. But the real energy transformation was radiant to heat. Now, I have a balloon inside of a balloon inside of a balloon. I have a red balloon on the inside, a blue balloon outside of that, and then a clear balloon on the outside. I want you guys to think about what you think is going to happen. Okay, you guys ready? Here we go in 3, 2, 1. I only popped one of them. I'm going to leave it for you guys to ponder. We'll maybe bring it back up later. All right.
Keep going. Okay. So last couple energy transformations today involve electric potential energy. And so the first thing I want to do is I want to take electric potential energy, and I want to take what's stored in this battery. So it's chemical energy stored as electric potential. I'm going to turn that on. I'm going to pass some current through this coil of wire, and I can make a little electromagnet. So this is electric potential energy, or voltage, into electric current. It's kind of fun. This is the same electromagnet, effectively. This time, instead of using a small battery, I'm going to use all 10 of these little blue capacitors. They're about the size of a pop can, and these are all going to store electrical energy. I'm going to discharge all of that energy through this little coil, making an electromagnet, and it's going to attract this roofing nail. These capacitors can empty the stored energy through that coil very rapidly. It's so fast that as that nail gets pulled into the middle, it shuts off the coil. And all that energy that the nail has got will continue. So I would like one brave volunteer. I saw red red sleeves over here. Come on down. Just in case. Go ahead and put those on. What's your name? Zoe. Okay, Zoe, what I need you to do, on the count of 3, I want you to push this button, all right? We'll just practice it real quick. It's going to make a little noise. Okay, 1, 2, 3. Beautiful. Okay, that's all I have to have you do. But let's go ahead and charge this all up. It takes a few seconds to store enough energy in here. Okay. I think that should be enough. All right, are you ready? 1, 2, 3. Well done. Thank you very much. Thank you. All right, thank you very much. That's the best shot I've seen in a while. Monika also talked about electric current through a wire generating heat with a light bulb. We also use that in a toaster. And the same kind of metal that's in the inside of your toaster, I have right here, a little piece of nichrome wire. When I put some energy into that, it should get hot. This one's a little more dangerous, but it's going to be electric potential energy stored in this big box. We've got a big capacitor here. Just in case. And when I pass that electric current, I'm going to store the potential energy, I'm going to release it as current. When that current goes through that wire, I should generate a lot of heat. I have to store more energy. It takes a little longer. Now I'm going to recommend that you also plug your ears for this one. I'll give you a countdown. All right. 1, 2, 3. Whew. So hopefully you also heard a little bit of sound. I hope. I actually learned about that when I was younger, playing around with electrical outlets. I don't recommend doing that. This time I do want to contain that release of heat. Thank you. And Monika just set this up for me. I have the same piece of wire. We're going to go ahead and put it in the back of this unassuming tube. All right. I think I would like a volunteer for this one. Way in the back, gray shirt. Come on down. Yep. Okay. Everything should be contained, but it might be loud. All right, so go ahead and put those on. What I'll have you do, again, on the count of 3, pull the pink cable just to test it. 1, 2, 3. Beautiful. Okay. Oh, by the way, what's your name?
I'm Mackenzie.
Mackenzie. All right, so Mackenzie's going to give us our final boom today. So hold on for a moment. Have to go ahead and charge this up again. 75 miles an hour, you think? Yeah. All right, earphones on. Are you ready? One, two, three. Hey!
Well, first, I want to also thank you for catching the ball. Very nicely done. All right, so in conclusion today, one, we hope you had fun. And thank you all for the volunteers. We really appreciate your help to make this fun. But a few takeaways. First, we realized that energy is the ability to do work. We identified that there were two forms of energy. There was kinetic energy, or the energy of motion, and potential energy, or the energy stored within an object. We saw that energy can come in many different forms and can transform many different ways. But the thing that you want to take away is that, as Einstein put it, energy can neither be created nor destroyed, only transform from one form to another, and it's up to you to figure out how to measure it. So thank you very much for your attention. We'll be taking questions shortly.
Okay, thank you very much, Monika. You know, we have time for questions. If people here would like to ask questions or explore in more detail how some of these things worked. But I first want to say that I was paying attention as you responded to many of the questions that Monika, Nick, and Conor asked you. And I think you deserve an A for all the... All right. We've also received a few questions by email. So, who has a question? Just raise your hands, and we'll have to bring the microphones around. Okay, I'm just trying to get an idea of what my route through the room should be. Can I have another mic? Oh, great. Okay, Roy's got it. All right. While the microphone is being transported, we have a question for you, Monika, which is, have there ever been any demos that go spectacularly wrong?
The short answer, yes. So we have one demonstration that is known as the killer capacitor. It got its name because it almost killed two professors. This was prior to us putting it in an insulated box. It's very similar to our Canon, but rather than one big capacitor, it has three big capacitors. And what one professor didn't follow our safety recommendations, and when he charged it, he went to go discharging it by going over the entire system to pull the switch. Well, electricity likes to find the shortest path to ground, and it happened to be through the poor professor. And so he did not die, but he was shocked and laid on top of this table for a minute while help arrived. It then almost killed the second professor because we put it in a box, but we used metal screws to secure that box. Well, the professor charged it up. He went to discharge it, and he was talking, and he had gotten close to a screw and close to the wire, and it went through his arm. Didn't kill him, but again, you could imagine the smell that was produced by that. We also had another notable failure, was when we used to have a spinning chair and a CO2 fire extinguisher. So what the professor would do is sit on the chair, put the fire extinguisher at a tangent or off to the side, and he would let the fire extinguisher go, and it would cause him to rotate. Well, it got stuck open. And so he was going and 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 going, and so when he stood up, he sure didn't feel very well after that. And so those are the most notable ones, but we get all sorts of failures. Occasionally, you know, we can never predict when a cable's going to fail or a battery's going to die or something's just going to break. And so The best thing that a professor can do is to understand that that may happen and to be able to show the world that they're human too and things can fail.
And I was not one of those
And you
professors.
were not one of those,
But I have my stories too. Okay, question.
What about the balloons?
Very good question. Very, very good question. So we see things in different colors, right? So what we're actually seeing when we see a color is the actual radiation that's bouncing off of that surface. That object is absorbing every other wavelength. So if you see something that's black, well, that is absorbing all the light. If you see something that's white, it's reflecting all of the light. And so with the balloon, when you have a red laser, the red balloon reflects that light. Therefore, it doesn't absorb it in order to heat it, so it doesn't pop. Versus the blue balloon, when you have that red laser, it absorbs it, causing that heat to happen, or that transformation into heat to happen, then making the balloon fail. And the clear balloon just lets everything go through it. It's transparent to color, and so that's why we don't see anything. And so that didn't get affected either. And so that is why the blue balloon popped, but the other two did not.
Okay, let's see another hand.
In your electrolysis experiment, why did you add, I think you said sulfuric acid? Did you need to do that, or would it have worked without it?
Thank you, Nick. All right, so thank you for the question. So the reason why we had a small amount of sulfuric acid, it's a 1% solution, is that pure water is a very bad conductor. For the electrolysis to actually happen, that current needs to flow. So you can add a couple different things. You could add salts, baking soda. For this one, we just use sulfuric acid.
When you were measuring the light with the radiance meter, so it had black and white panels. For a moment, I thought that the black panels would absorb the light, the white one would reflect, and that's what would make it rotate. But you said instead it's a thermal gradient that made it rotate. Is it possible for it to rotate in perfect vacuum just from the light bouncing off of it?
That is a wonderful question. And so there's actually a number of YouTube videos going into a lot of detail with that. So the person who invented the radiometer thought that it was indeed the light hitting the vanes that caused it to rotate, therefore it would work in a vacuum. But what they found was the friction in the system and all that is just much larger than what type of momentum that would be imparted by the photons, which again, that's not the mechanism that worked. So it turns out that the edges of those vanes are what heat up, and that movement of that little bit of air inside of there through the mean free path length of that gas, again, a very complicated situation, but essentially that heating on the edge causes that movement of the gas, which then imparts on that rotation.
Are there any more questions from here?
So going back to the spring, and assuming you have a spring on a pendulum, what could you apply to the spring to make it less springy or more springy?
There are a whole host of ways to damp oscillations. One of my favorite low-tech ones is filling the inside of the spring with sponges. You could also put it in a liquid. We do a series of damped oscillations using glycerin.
Is there someone that, like applying a current, like something that could be turned on and off, to change the properties?
So we also have another set of oscillators that is a current carrying coil. It's actually one of these. And so you can run this with a function generator and actually put a magnet as the mass. And so you can tune the oscillation of the spring using the current to do that.
The one problem with springs is it's really a material property. And so the spring constant of that material is what governs how springy it is. And so without being able to modify that material property, generally objects have that given frequency of oscillation. And so you kind of are fighting that when you want to just damp a specific spring. But an example of how they might use those properties, gravitational wave LIGO experiment. I'm sure some of you have heard that. That instrument is so sensitive that it can pick up a car driving by the facility as they're trying to make that really sensitive measurement. And so what they do is they put the mirrors of so they send a laser, they split it, they go and recombine it and look at the oscillations. One way that they help damp the oscillations that might exist in the mirrors is they put a series of different types of springs connected to each other so that an oscillation in one won't transfer to the oscillation of the next one, therefore allowing the object to stay stationary. So you kind of have to, rather than manipulating the specific spring, you have to come up with a more complicated way to deal with that damping.
That is a really interesting question, and I'd say had me stumped as well. But Monika's right, it's a material property, the way material springs work. I guess, and Professor Clark may be able to add something to this, there are materials that respond both electrically and elastically, piezoelectric materials, and it may be possible to tune, as you're discussing, the spring constant or the bulk modulus of a material in that way. Professor Clark?
Yeah, that's right. And it's also an inverse effect where you can press on a material and develop an electric response. Electric energy is transformed by the motion. So that works both ways. The common gas lighter that Monika used actually works that way. You press it, creates a spark, and then lights the gas. So.
That is also how we actually measured the vibration on our cup with the same type of piezo pad. When you squished it, electricity was made.
Okay, here's another question.
No friction. That's not ice.
A cushion of air works really well. Superfluids, yes. So it's not a common property. In general, you just want it to float on top. So ice works because the very top layer of ice is actually water. And so it allows you to slide.
And then at very low temperatures, helium gas in particular has very interesting properties and becomes frictionless, basically. It's called a superfluid because it's so super. Oh, okay. Sorry.
Thank you. Can you say something about dark energy and how to measure it?
What?
Dark energy and how
Arc
to
energy?
Dark.
Dark? Oh, dark energy? So that is not my area of expertise. I don't want to answer this one. I'm not confident enough to explain that one, but maybe Tim would have some insight.
Okay, so there's something called dark energy. There's also something called dark matter. Both of these are not normal matter that we're made of. And dark matter has gravitational attractive effects. And there are attempts to measure that. If it interacts with matter, then you build a detector out of material and see if something happens in that. Dark energy was observed or discovered by measuring the rate of expansion of the universe at different distances. And as we can look further and further away and calibrate those observations, it's been determined that the universe expansion actually has been speeding up. So that's the detection of dark energy, that astronomical or cosmological observation, and not any laboratory type of experiment. So dark matter, yes. Dark energy, not yet.
Over here, You demonstrated generating electricity through the bike, rotational motion of the bike. Why don't they use that same technology in terms of generating electricity for vehicles?
So they do a bit of that with regenerative braking in a lot of hybrid cars. And effectively, all you're doing is taking the electric motor that's powering the vehicle, letting the car's momentum drive that motor as an electrical generator. You're just switching the wires and powering the battery that way. So it's not a way to recover all the energy, but it helps a lot.
Well, this is the principle of what's called eddy current braking, and that's exactly what Monika did. And those are really important in trains, and again, maybe in some cars. I'm not sure about the engineering of that. Maybe somebody knows. Oh, yeah, that's right. Exercise bikes are lots of ways to generate the friction. Okay, here's another question.
With the wine glass demonstration, is there a way to capture the glass in the flexed, version, where it's stretched out?
Could you repeat that?
All right, yeah, go ahead.
So with the wine glass demonstration, when you put the sound up to it, it kind of flexed out. Is there a way to capture the glass in that moment?
So you were, I believe this is your question. Let me try to reiterate it, which is that you showed the wine glass flexing, right? And then it broke sort of catastrophically, and you want to know what it looked like exactly at the instant it broke. Is that correct? Okay.
Oh, okay. So if
Yes.
you were to remove the speaker that is tuned to the frequency of that the glass's natural frequency, it would go back to its normal state. I don't believe there would be any sort of distortion unless the glass has already cracked or had been broken.
Basically, that stored elastic energy that pushed it out would go back to, it would lose that immediately. Good question, though.
Bones do that too.
Yes.
up to a point. It's very important for us. Okay, other questions? We do have a few more minutes.
I have a question for you guys. What was your favorite? What was your favorite energy transformation?
My favorite was the tennis ball cannon.
Tennis ball cannon. Very good one. Very good. How about you?
My favorite one was the hydrogen explosion one.
Very nice. Very nice. Any other different ones? Yes.
My favorite was when you shot up
The nail. Very nice. Yeah, that was a good one too. Wonderful. I'm glad that they were all a little different. How about you? The bike generator? Yeah. Great.
Here's a question. Are the wine glasses very expensive?
So we use white wine glasses instead of red wine glasses, but really anything with a resonant tone will work. So I don't choose the most expensive because they are destroyed each time. And so I get a box of 12 of the Libby brand glasses. And the one problem with getting cheaper ones is they're not 100% consistent. And so we actually found that standing waves will, if the glass isn't completely uniform, the standing wave that's produced in the glass is not uniform as well. Therefore, there are certain orientations that the glass ends up working better than others. And so if we were to spend the money and get, $40 glasses each time, wouldn't matter. We could just throw it in front of the sound or the speaker and it would work great. But because I go for slightly cheaper ones, because unfortunately they come very unusable after, we do have to compensate for that lack of quality control.
Is it true that a human voice can generate the energy to break a glass?
Yes. So the hard part is you actually have to hit that resonant frequency. And so a very well-trained person or a very lucky individual can hone in on that frequency and break the glass. Ones as thick as this one would be pretty hard-pressed, but those really nice red wine glasses that are very thin, absolutely.
I think Maria Callas was the first person to demonstrate that. It was a famous opera singer in the 1960s.
I believe Ella Fitzgerald has done it too, as I recall. Was it Ella or was it Memorex? Okay. One last question. Can anybody else ride the bike?
Does anybody else want to ride the bike?
All right. Well, for those of you who don't dare, thanks very much for coming, and come on down.